Okay, so today in this video we're going to be talking about specific heat. Before we get to specific heat, let's take a look at this warm-up question and see if you can figure out the answer based off of the notes you've gone over in the past and the last few videos that we've done. Okay, so the warm-up question says, which of the following statements regarding thermodynamics is not correct? And the answer choices are A, the pressure of a gas is a measure of how frequently the gas particles collide with the container walls. B, the temperature of an object is related to the average kinetic energy of the atoms or molecules making up that object. C, the second law of thermodynamics states that entropy of a system naturally tends to increase. And D, the freezing point of water in Celsius is 32 degrees Celsius. So, three of those are correct. One of them is not correct. See if you can answer this warm-up question. Okay, so hopefully you got the correct answer. The correct answer is D. The freezing point in water, the freezing point of water in Celsius is actually 0 degrees Celsius. Okay, so in the Celsius temperature scale, water freezes at 0, and it boils at 100 degrees Celsius. Now, it is true that the freezing point of water is 32 degrees Fahrenheit, but that's a different temperature scale. Okay, so the correct answer to the warm-up is D. Okay, so moving on, today we're going to be talking about a new concept. In the past, we've learned that there is a difference between thermal energy and temperature. Namely, that thermal energy is the total kinetic energy of all of the atoms or molecules making up an object, whereas temperature is a measure of the average kinetic energy of all the atoms or molecules making up an object. And so we've looked at questions in the past where we had 2 cups of water, both with the same temperature, meaning they both had the same average kinetic energy in their molecules, but one of them had more thermal energy just because it had more atoms. And so, obviously, different types of materials behave differently when you add or remove heat from them. So, today we're going to be talking about one of the ways that we quantify how different substances respond to different amounts of heat, using the concept of what's called specific heat. Okay, and there is an equation for that. We will see that momentarily. First, let me just give you some definitions. We know when energy flows into a substance, and in this case we're talking about thermal energy. When thermal energy flows into a substance, the amount of temperature gain is dependent on the properties of the substance, because as we talked about before, different substances are made of different types of atoms, and they have different numbers of atoms, and so on. In other words, not all substances gain or lose heat at the same rate. So this is where the idea of specific heat comes in. The specific heat of a substance is defined as the amount of heat needed to increase 1 kilogram of that substance by 1 unit of temperature. In other words, by 1 degree Celsius or by 1 Kelvin. Okay, so that is the definition of specific heat. Now, on the next slide, we will see an equation to do calculations with specific heat. But if you look at the definition, the amount of heat needed to increase 1 kilogram by 1 degree, that's basically what specific heat is. In other words, the bigger the specific heat of a substance, that means it takes more energy, more heat, to raise the temperature by 1 degree. Okay, so keep that concept in mind. Now the equation we're going to be using looks like this, and you might have seen this equation before. Okay, this equation is Q equals mc delta T. Okay, I know it's on the slide, but I'm just going to write it out here to the side. Q equals mc delta T. Now, I don't know why it appears like an uppercase C on this slide. Typically, specific heat is written as a lowercase c. So in this equation, we have Q, which we've seen before, that is heat, and that's measured in joules. We have M for mass, measured in kilograms. We've seen that before. We have C, that's the lowercase c, sorry about my handwriting, and that is specific heat. Okay, now the unit for specific heat, which you typically don't need to worry about too much, but the unit is joules over kilogram Kelvin. Okay, joules per kilogram Kelvin. And then right here we have delta T. Now, anytime you ever have a delta, that means you have a change in it. Okay, so delta T, in this case, this uppercase T stands for temperature. Okay, so delta T is the change in the temperature. In other words, the final temperature minus the initial temperature. Okay, so this is change in temperature, and that's measured usually either in degrees Celsius or Kelvin. Okay, but again, delta T, you can expand that out. Anytime you have a change in it, it's always the final value minus the initial value. Okay, so just keep that in mind. The equation is written with the delta T, but most of the time we're going to have to plug in two temperatures into this equation. Okay, so this is our equation for doing problems with specific heat. Now here's basically what this equation says. Okay, basically this equation says if you add this much heat to an object with this mass and this specific heat, its temperature is going to change. Okay, likewise, if you have a negative heat, in other words, if you remove heat from an object, given this mass and this specific heat, the temperature is also going to change, but it's going to decrease in temperature. Okay, so this equation basically allows us to connect how much the temperature changes based off of how much heat that we add or remove. Okay, so that's what we're going to see now. So I'm going to erase what's on the slide here, and we're going to look at some examples here in just a minute. Okay, so first I want to show you this chart. Typically you're given a chart or a table to do problems with specific heat because different types of materials all have different values for specific heat. So here on this chart we have the specific heat for aluminum, for carbon, for copper, glass, methanol, lead, ice, and liquid water. And you can have much bigger tables with, different specific heat values. This is just to give you an idea. Now, if you look at what it says in the notes, it says the higher the specific heat, the more thermal energy is needed to raise the temperature of an object. Thus, an object with a high specific heat will take more heat, and usually a longer time, to heat up and cool off. Okay, so for example, if you look at lead has a specific heat of 130. And if you look at this chart, you'll see of all the different materials on this chart, lead has the lowest specific heat value. Now, what does that mean? Basically, that means, in simple terms, that lead is the easiest of these materials to heat up. Okay, that means if you take the same amount of thermal energy and you apply it to, an equal mass of all of these materials, lead is going to change its temperature the most. In fact, if you look at the other low ones, you've got lead, and you've got copper, aluminum. Metals tend to have a very low specific heat. Meaning that metals tend to change their temperature very easily. And so we'll talk about that a little bit later, but that's one reason why cookware is made out of metal, because if you put let's say a glass pan on the stove, glass has a much higher, or not glass, let's say carbon or glass, which are non-conductors, have a much higher specific heat compared to, say, lead or iron, for example. And so that means they're not going to heat up as easily. So let's take a look at an example. We're just going to do a very basic calculation with our equation. Example 1 says how much heat must be added to a 50 kilogram sample of lead to increase its temperature by 100 degrees Celsius. Okay, so first we need to identify our givens. How much heat? Heat is Q. Remember that's measured in joules. Must be added to a 50 kilogram, so this is the mass, sample of lead to increase its temperature by 100 degrees Celsius. Now keep in mind, it says to increase its temperature. It doesn't say the temperature is 100 degrees Celsius, but that it increases by 100 degrees Celsius. So this is going to be our delta T. Now the fact that it's lead means that we can look at our chart over here, find the specific heat of lead, and then use that for our problem. So if we want to find Q, we have our equation Q equals mc delta T, and all we have to do is plug in our values. Okay, so this is a very simple calculation. We have m, which is the mass, that's 50 kilograms. We have the specific heat of lead, which is 130. And then delta T, the change in temperature in this case is just 100 degrees Celsius. Okay, so if you take your calculator, plug those values in, 50 times 130 times 100, you get 650,000 joules. Okay, so that is how much heat it takes to increase the temperature of a piece of lead by 100 degrees Celsius, which is quite a lot. But then again, it is a pretty big piece of lead, and that is a really big temperature increase. Okay, just to give you an idea, 100 degrees Celsius, that's basically increasing the temperature by more than 200 degrees Fahrenheit. So that's quite a big amount of energy it takes to do that. So that is example 1. Okay, so example 2. How much heat is released when a 0.45 kilogram piece of aluminum cools from 45 degrees Celsius to 15 degrees Celsius? So now we have to do a little bit more work. Remember, heat is Q. Now, whenever heat is released, that tells you that Q is negative. Okay, so a negative value for Q corresponds to heat being released. Just keep that in mind. In other words, we should end up with a negative value. Now here we have the mass of the aluminum. Because it's aluminum, I have the specific heat value in the chart right here. And it says it cools from 45 degrees Celsius to 15 degrees Celsius. So remember, in the equation we have mc delta T, and delta T, the change in temperature, is the final temperature minus the initial temperature. So we're always going to have two temperatures typically. To figure out which one is which, you just have to use context clues. If it goes from 45 degrees Celsius to 15 degrees Celsius, this is the temperature it starts with. That's Ti, that's the initial temperature, and it goes to 15 degrees Celsius, so that's going to be Tf. So from here, all I have to do is take my equation and plug in my values. I have the mass is 0.45. Specific heat of aluminum I get from the chart, that's 903. And then delta T, I'm going to expand that out. Remember, delta T is T final minus T initial, so that's going to be 15 minus 45. Okay, so take those values, plug it into your calculator, and let's see what you get. Okay, so if you did it correctly, I believe you should get negative 12,190.5 joules. Okay, so that is the answer to example 2. Keep in mind this is a negative value, just like we predicted, because heat is being released. Okay, so pause there if you need to. Okay, so let's move on. Example 3 says, when 5,000 joules of heat is added to a glass bowl, the temperature of the bowl changes from 24.5 degrees Celsius to 30.2 degrees Celsius. Calculate the mass of the bowl. Okay, so now I'm going to go a little bit faster. In this case, I'm actually given Q. Okay, so 5,000 joules of heat, that is my value of Q. It's added to a glass bowl, meaning I can use my chart. Here's a glass. It has a specific heat of 664. And it says that the temperature changes from 24.5 degrees. Okay, so that's going to be Ti to 30.2 degrees Celsius. Okay, so that's going to be T final. And the unknown is, it says to calculate the mass of the bowl. So again, I take my equation, Q equals mc delta T, and now I'm just going to plug in. This time, instead of solving for Q, I have to rearrange and get mass by itself. So Q is 5,000. Okay, the mass is unknown, so I have to leave that in the equation. For C, I'm going to plug in that 664 from the chart. And then for delta T, for the change in temperature, that's the final minus the initial temperature. That's going to be 30.2 minus 24.5. Okay, what I'm going to do now before I solve for the mass is I'm going to simplify the right side a little bit. I can clean this up because I can actually simplify what's in the parentheses. I can do 30.2 minus 24.5. You get 5.7. And then if you do 5.7 times 664, you get 3,784.8. And remember, that's being multiplied by the mass. Okay, so in order to get the mass by itself, I'm going to have to divide both sides by this number out front. So I divide by that 3784.8, divide by 3784.8. That's going to cancel out. And up here, I will write down the answer. Okay, if you divide that correctly, you should get the mass is 1.32 kilograms. So that is example 3. Okay, so those are just a few basic problems involving specific heat. Later on, we'll do some more complicated ones. Okay, so pause there if you need to. Okay. So, we're just going to take a look at, before we do example 4, I just want to talk about this really quickly. Some general trends. We talked about this before. Metals tend to have a very low specific heat, meaning they change temperature readily. Readily means easily. Okay, so we talked about this before. This is why cookware tends to be made out of metal, because if you put a pan on the stove, you want it to heat up very quickly. If you put something that has a high specific heat capacity, such as water, it takes a long time to heat up. Water actually has a very high specific heat capacity. It's over 4,000. As a matter of fact. So what that means is, let's say you take a metal pot, you fill it with water, and you put it on the stove. The pot is going to heat up way faster than the water because the water has a way higher specific heat value compared to the metal pan. Okay. Now, here it says liquid water has one of the highest specific heats known, which in general is a very good thing. Why do you think this is a good thing? The answer is given at the bottom of the slide. Basically, it prevents large fluctuations in temperature of the oceans from day to night. A lot of our weather patterns, and if you think like tsunamis and hurricanes and stuff like that, are caused by temperature fluctuations in the ocean. Because the ocean is filled with water, which has a very high specific heat value, the temperature of the ocean is pretty stable for the most part. If water had a low specific heat capacity, that means that the temperature in the ocean could change rapidly, from night to day, and cause, crazy storms all over the planet, and which would be bad. Another benefit of water having a high specific heat value is that it prevents large changes in body temperature. If you think about your body mostly being made of water, typically humans, you want to be around 98.6 degrees Fahrenheit. The fact that we're made of water and water has a very high specific heat means that it's not that easy for our body temperature to change, which is good, because otherwise, we might not be able to exist the way we do now. So that's just some concept stuff related to specific heat. Now, example 5, there are a few more examples, but I think I'm going to stop here and continue. We'll do the more complicated examples in the next video over specific heat.